Oh, yeah, good. Trees are costs or the assets. As I mentioned before, the trees are often managed as part of urban maintenance systems with well established estimate of electronic benefits, as we see here. Today, we want to use housing price as a sensor. The property prices act as a high sensitivity materials prox, which means it can capture the residents' willingness to pay for the localized ecological amenities. Let's go to the next level about the data. Yeah, so the 43 points we got from OpenData, of course, and also the NYC citywide annualized calendar sales update, which is housing transactions. They're all from OpenData. Nice. And yeah, how can we build the valuation system? Is there a relationship between them? So we have to consider all the other factors that might affect housing price. So here we build a model with use a house as in, and we care about the surroundings. So first level, we have a buffer level with 50, 20, 200 different meters. The buffer can include different numbers of amenities, especially the POI, points of interest, like the restaurants or the hospitals, like how actively the neighborhood is. And we also care about some data from CBG level. So CBG here is census block group. It is level from our census data. From top to down, maybe we care about, it has the county. So it has census block. Then the census block group is the smallest level that we can get. We want the data can as precise as possible so that we can involve the social economic status data in and together is with our house. We control for neighborhood social economic factors to prevent overestimating the green premium and ensures accurate evaluation. So from step to step, we have the housing structures information from here. Of course, like how many units are there, what is the areas, and we have the tree data. Of course, we care about that. And other amenities, the social, economic, and the administrative. In the end, we build our data site with 41,000 housing transactions. By the way, this is from 2023, and we have 50 variables included. And yes, trust me, this is the last slide about our data set. And we really spend lots of time for people who work on data, and you have to do a lot of dirty jobs to do the cleaning. We care about two things for sure: the building cells and the trees. I listed here. And we cared about the features that can have the impact over the building cells, which means they will make some contribution to the housing price, either positive or negative. And we have other variables, as we mentioned earlier, and these are the sources, and they are all open data. Just to stress it again, we have two different levels. The first one is that levels are decided based on our data features. So first we have different buffer levels. We choose 4 scales, which means 50 meters is very close, and 80 meters is the half mile, which means that is maybe the utmost distance people might want to walk. And we unify the projections, of course. Next, we have the CBG level, the census block group level, and we will unify them with the index. For so far, New York City has about 5,000 census blocks groups. So here we are, we got all the data we want. Yeah. So before we step into the model, let's do a little bit final check about the data quality. So here we do have to implement some data pre-processing to the housing price and the three trees data. So from the original data I showed here, we can see the housing price is very skewed. it only has very maximum numbers and only limited minimum numbers. So we have to do the log scale data pre-processing. After doing the log, it is better. It is almost look like a perfect normal distribution. So we think, yes, we got good data. So that is proof that we can continue to our next step. And here we have another plot shows the distribution of the street trees. Yeah, it is normal distribution, but it's not perfect, which shows maybe across different neighborhoods, different area, the tree will have rows bars across the numbers. So I add here the clear clusterings of low and high trees canopy census block group. Yeah. So yeah. If you have any question, just please mention that. And next, we will go to our modeling integration. So from the global trends to local variations, after we do the data pre-processing for all the variables, we do care about if it needs to be a log scale or it is categorical variables, and we need them to be dummy variables. And also we have to do the serialization, lots of stuff to make sure we can put them in our model later. And here I use XGBoost. As I mentioned earlier, we have 4 different scales. We do care about which scales has the best performance because somehow we cannot put all the 4 scales into one model because it will lead to the multi-collinearity issues. After doing the XGBoost, we got a good result. The best buffer is 400 meters. We will explain it later. And also, we do the variable inflation factor check, which means we will remove the multi-collinearity variables in a further way. In the end, we got the refined covariates. And from a traditional way, we can do it with OLS because it is a very straightforward way to measure the contribution of street trees. Like you can just see the coefficient of it and tell people, see, this is a contribution, positive or negative numbers of a tree. But it has a limitation here. So OLS has the averaging trap, and which means it will give a global coefficient for all the trees across New York City. It cannot capture the very nuance between neighborhoods, between boroughs, which means a house in Manhattan will have similar kind of results, the tree contribution results from the house in City Island. So that is not good. So we do the Moran's test, and we found out that based on the number, has a lot of geographical issue, and our research will mainly focus on the geographically weighted regression. With this model, we can build a spatial heterogeneity of green premium, which means the model in the end will be contextual and it will be able to identify the heterogeneous. And here, about the XGBoost, I have several interesting findings to say. And XGBoost, we use it here as a scale discovery or nonlinear validation. And first, as we mentioned before, the buffer equals to 400 meters is the best model, which means, we decided with the R square with a 10-fold running. And it is good for me, at least, because the scale represents the 5 minutes walk threshold, because you can see, on the neighborhood with 5 minutes walk distance will affect my living conditions. And the second thing interesting here is we can capture the nonlinear relationships with machine learning. So here we capture the x-axis is straight trees in 400 meters scale. And the Y scale is our predicted logged housing price. So we found a U shape here, which means it is not linear. We do care about the two things here. The lowest point is a threshold, 223 trees, which means before this point, the trees across your neighborhood might be the cost because they will generate some branches, they fall down or they break your windows, so many other considerations. But after that, once it become a canopy, and it will bring some positive effect to your neighborhood. And we care about the second number here as a turning point, which means it will turn the relationship here will turn to steep, and which means it shows the critical mass. The number here is 645 trees. The third thing, maybe you care, maybe you not. We are predicting the housing price, right? We have so many variables here, so why not we just run a sharp map to show a sharp plot to show what is the most important factors over the housing price. So we see here the residential unit counts and the total building area, educational attainment are the top three, which means the scales and the education drive fundamental values. Sadly, the tree economy, the three trees is not on the top 10 or even the top 20. We will say the tree economy may provide the hidden incremental quality of life premium. Yep. Next, we do the VIF, the variable inflation factor. As we mentioned before, we don't want the multi-communality at all. What did VIF do here is you only keep the as precise as possible the variable here. As I put at the example I put here, we have three variables: total area, lot area, and the floor area ratio, FAR in short. We remove the total area and keep the other two. We can do the other way. And the reason here is we can easily tell the total area has some relationship with the lot area and the floor area ratio, which means if it contain all the three variables, the coefficient of total area will be distributed by the other two variables. Since they do have some correlation, they do have even a mathematical formula here, so we don't want the coefficient to be changed. So in the end, after doing the VIF validation, we got independent variables for our geographically weighted regression model. As people care about here, initially we have 50 variables, actually even more after we do the data processing, do the categorical one-hot coding. And in the end, we cared about 26 multi-granularity features here, which means we only keep the VIF over 10 features. And we can categorize them into four parts. The first is the physical, like the building structures. Yeah, the numbers of floors, the residential units, things like this. And also the institutional and the zoning considerations. It is also inside the housing transaction data, and the property tax category and the commercial zoning zones. And it belongs to one category, and you can tell the residential zoning intensity as together with it initially. And the third is a social economic status about a house, your neighborhood, like what are your neighbors matters, like their median household income or education attainment. They are important, or we can say, yeah, they are actually have positive correlation with the housing price. In the end, we have the environmental amenities here. Yeah, we definitely have to keep the street trees count here, the number of street trees within 400 meters buffer. and the tree canopy coverage, the park accessibility index, amenity accessibility, yeah, so and so on. I believe this is the last part of the modeling integration, and after that we will see some results. And if you are in the forestry area, there is a famous quote here. I was under the impression that all people like to have trees planted in front of their houses until I started planting trees in front of houses, which means the willingness of planting trees, or we say the price of a tree will be very so different across different neighborhood. It has very strong heterogeneity. So we compare the OLS we mentioned before and the GWR again. As I explained earlier, the OLS can only capture a global coefficient for the variables that we care about. But the GWR's superiority, which means it can capture the coefficient across the whole New York City. And with the plot I showed here, we can get a map, ideally, which means the core area may have a high density premium, and the boundaries might have a very different performance. Yes, and this is our GWR's results. Before we dive into the actual numbers, we have some parameters to introduce here. Before we run the geographically weighted regression, we need a parameters named the bandwidth. So the bandwidth here, we choose the adaptive K. The K means the number of your neighbors. For example, our result of K here, it is a 3,923, which means almost 4,000 of your neighbors out of our 35,000 samples. And that K represent the neighbor around you. You share the similar situations. You share the similar status. You share the similar coefficient of the street trees, which means it is a auto-adjusted search radius across diverse urban densities. It not just cared about the difference between the Manhattan and State Island, and we can see it further. Some interesting thing here, like in New York, like the Manhattan area, it is very dense. The housing there is very dense. So, which means the similar number of K, which means your neighbors, might represent a smaller scale. So we can see here the Manhattan is a borough, and it has a minimum. We calculated the K, the numbers of neighbors, into the local search radius. It is about 2 kilometers, and that number, if we put that scale into State Island, it turns almost 10 times, which means across different boroughs, not just even have to be different cities. We can see the heterogeneity across the neighborhoods. And the last result, we check if it is a good result for us, if it is useful. So we do the robustness check. The moron here is around 0, which is good, and the p-value is over 0.05, which is significant. Yep. And as we mentioned earlier, the GWR has some superiority over the OLS. It has better predictions, which means that the R square is better. We can see the efficiency leap here of GWR. It goes from 0.33 to 0.4. The GWR performs OLS by capturing spatial stationarities. And the second thing is about the R square. There is spatial variance. Even we do it in a spatial way, the GWR is still a regression, which means they have different coefficients. So each coefficient will have an R square. And we see the R square. It is the R square's map. It is colorful, which means even we got a very good result about Manhattan area, but we have to take care because the R square here is not ideal, which means the variables we select for the Manhattan area only have about 20% of explainability about the housing price. I think maybe this is most of the thing we care about today, the coefficient of the street trees. And what does that mean? How can we link that to the reality? Remember, we earlier do the log scale process over the housing price. And we do the z-score standardization with the street trees. So we have to put them back to use this formula to calculate the real impact of the coefficient. So here we can see the results. If we got a coefficient with positive 0.05, which means the changing poverty value will have 5% with we plant one standard numbers of street trees. So this is the explanations. It is almost at the end, and we have our. Oh yeah, I can go back. Nice. So we have our policy view. So how can we build bridging this data and a policy and translating the tree premium into budgetary priorities? We will show you a website later. So here we have 3 layers. The first is our evidence level, which is the data points. There are dots, and they are our data input. We use a GWR, our model, to identify the premium area. And in the second, obviously, we have different levels. The census block group, it will be seen as an analysis level. It has so many socioeconomic status, which will link the neighborhood and give the people a better sense of what does that neighborhood look like. And for a community planning, they can use it as to support the report. In the end, we have the third layer, the policy level. As we mentioned earlier, the New York City have 59 community board. And for all the community board, all have their own website. They will do their planning for the next year. They will say, okay, so our top 3, our goals in 2026, we will be build the Hutchison River Parkway. This is from the Bronx Community Board 10. And I showed it here. Yeah, we cannot say the street trees can be considered a next move over the community level because street tree somehow is very small. So I think to engage to attract more as much as possible the money to their community, they have to mention some plan bigger. Like the Greenway will be a good choice. It is not from the park, but it has some positive the environmental benefits for the local residents. And here, if you're interested, you can scan this QR code. And sorry, I didn't do the phone adaptation. So you have to rotate your phone a little bit to test the different layers. You can see the different levels I mentioned before. First, of course, the community board, and then the CBG level. You can see the census, the social economic status across your neighborhood or the neighborhood you are interested in. And in the end, see the house. So each dot will represent, I should open it. Yeah, so this is the 6. Okay, so this is community district 10. Oh, wow. It's aligned with the neighborhood. Here, the Strogs Neck, Culper City, and City Island. Overall, it has a positive coefficient from the street trees. They dig inside, they're all positive. But for area like this from Queens, it looks very balanced from a community district level, but we dig inside. Yeah, it has both green and red, which means the readout will show a balance, but inside it have very even performances. Yeah. Let me do it. Yeah, here you can see the coefficient R squared, the representation for the numbers. And let me go back. Oh, I think. Oh, what? Wait. Oh, yeah. Okay. I think we are almost there. About this project, we have some preliminary key takeaways. So the first thing, the scale of perception is 400 meters. From the XGBoost model we ran, 400 meters will be seen as the human-centric buffer. And the second thing is we have a spatial heterogeneity across the New York City over the contribution of street trees on the housing price. We will use the geographically weighted regression as a diagnostic sensor to build a tree valuation system. The third thing is the equity gap. The tree premium as a wealth catalyst. Yeah, it has some benefits, but it can be a cost, a burden for a neighborhood. The first thing is the evidence-based policy. As we showed earlier, the very able to move unit is community board. They have the right to propose something, to make some act, to make something happen. So from the intuition to quantifiable ROI, we have some suggestions with our map. So the community board, yeah, these are the areas that we might be cared about. And the last thing, about our website, we really hope that can be used as a tool to see the street trees as microgreen spaces. We do have some next steps. Trust me, this is the last slide. And of course, there are limitations. And as we mentioned earlier, the XGBoost, we run a U-shape, which means it is non-linear relationship between the street trees and housing price. But the GWR we run, it is actually still a linear regression. Beyond the linearity, the critical mass threshold will give us more information or more evidence to set different parameters for our next model. And also the fixed buffer will ignore, like our fixed buffer here is 400 meters. It will ignore the urban morphological diversity. We ask for nonlinear model to explain. If we add random forest, the machine learning after the geographically weighted model and link them together, we can do the machine learning in a special way, and it can capture both the heterogeneity and the nonlinear relationship. And also the neural network you can do to capture the nonlinear relationship. The third one is from asset value to social equity. We currently do care about the owners, but we haven't know what will the renters thoughts. I might not have the chance to buy a house in New York City, but as a renter, I think I still care about the trees around me, the green space, and maybe we will make the data, will expand the data into a bigger scope. And the last thing is the correlation between the trees and the housing prices. We are actually still doing a association research, not a causation one. In the next one, we can build some causation model with the DAG to explore some more nuanced relationship between it. Okay, I think that's it. Thank you so much. Thank you so much for focus. Thank you, really. If you have any questions, please.
I think we have a question from the audience, Laura. Laura asks, Can the model differentiate between apartments and houses?
That's a good question. So far, we cared about housing from a coordinate level, which means it is not a polygon. It is a coordinate. And we build all the buffers. We do all the aggregations based on the coordinates level with only latitude and longitude data. But about this question between the apartments and houses, I think the building cells data, it has some features. I should go earlier. Yeah. Oh yeah, here. So the building cells has a lot of features, and I remember one of it. Maybe I didn't put it here. So it shows it is it is a apartment or a house. It is a single house. It has different layers. It has different units. I think that will answer the questions. So in the model, we did put so many different physical features about a building into the model. I believe we capture the difference between the two. With our 26 features in the end, we have numbers of floors, residential units, lot area, and the floor area ratios. Yeah, I don't know if that answers your question about the difference across apartments and houses. Yes, is it good, Laura?
I'm not sure I fully understand because the what you're removing is total area, but you're keeping the lot area, and you refer to that as, do people have yards? And many apartments do have yards, and maybe they're communal, but when you average it out per sale price for individual apartments, it's going to be much smaller. So I'm not really sure how the model accounts for things like that. Maybe it does, but it's just too complicated to explain here.
Okay, so you mean the price across apartments and houses are different?
Yeah, I think initially what we wanted to do is to account for the residential areas, but this is the data that has a lot of missing information in the original data set. So we account for the lot area instead. Is that correct, Archie?
Yes, I think the feature we selected here more from a model that we want to avoid the multi-collinearity. So we remove some of the features because it will generate some impact that we don't want to see in the model. So we remove them for the model consideration, not just from the knowledge we have in the daily lives. So I guess the lot area is imperfect feature we are currently using to represent the housing area.
The lot area, are you using the actual square footage of the tax map lot? Or are you using the buildable area? Because certain lots you can only build on 65%, certain lots you can only build on 100%. And I think that might factor in whether there's yards or not, whether you can build out all the way to the lot lines or not.
I think we're talking about the lot size we are using in our model. And yeah, that was a great point from our audience. So definitely something we can incorporate in our next steps regarding whether we're using the whole lot size or the buildable areas in our model. Yeah. Thank you.
Yeah, because part of it is in the areas that had the most green dots, those are areas with lower density and already have large parks with a lot of trees and already have buildings that are older and have bigger side yards. Current zoning reduces the amount of yard space for new buildings. So that might help you adjust it to what's current. The city of Yes that was passed that we didn't like.
Got it.
Great point.
Yeah. Yeah. So I think across our variables, all of our features have interactions. And currently, we only care about the single features. We haven't considered the interactions between 2 or 3 different features. So yeah, thank you for your suggestion. Ray, you mentioned, is there any data available to distinguish between a condo and a rental apartment in New York City and you probably didn't use it, but I wonder if such data exists. So I think the housing data we only use NYC citywide annualized calendar sales updates. Does it have a condo or a rental apartment? I think the answer is no, because we only care about the housing transactions, which means they make a deal, not a rental apartment or a condo yet. Yeah, I think we tried to search the data before, but I think we failed, or somehow we want to focus on the transaction first. Yes. Any other comments? Yeah, please.
Um, Thank you for your presentation. This is awesome. I was just curious. I know that you said that you used the tree census data. I was just wondering, does the model take into account like tree size, like the diameter, like breast height, or other aspects just because of the count of trees? I know that like you also use the canopy coverage, so that
Yeah.
may impact it, but I know that the like count of trees sometimes can be misleading in the terms of like how much size or impact they have.
Yeah. Okay. Okay. Thank you. Thank you for your question. So my answer is not yet. We haven't covered the granular features across the tree, like their species or how big, especially their age, like how big they are. We haven't covered it yet. I think that is a more granular way because inside our data, we are not able to, we currently only consider the numbers of the trees across a buffer. I think that question matters for a community level. We might not be able to solve that from a data level because I think the community they mentioned for so many trees, they are in established period actually, which means that the New York City parks, they build the trees, but no one knows. So during their long 3 years established period, some tree will die. About this part of trees, it's very hard to capture their changes. And about the big trees, I think the tree canopy we add here, may think it will cause the multicarnality we mentioned earlier, but actually we think, yeah, as you mentioned, the tree canopy, it will have a different expression over the numbers of trees. Yes, so I think that is it. Thank you so much.
Thanks for the presentation from the American Institute of Management. And I wanted to follow up the comments about the differences between apartments or houses. I think the biggest issue here is that you're using total value of the sale per square foot estimates that will solve a lot of those problems. Because right now you are and looking at your map, coming between Upper East Side, Upper West Side, Upper West Side, you don't have your big huts, but also lower. But it might be the effect of the size of the apartments or houses being sold. And,
Yes.
and that also affects your distribution of the sales values. I would basically somehow try to adjust or not adjust, I would basically switch the dependent value of the kind of. So you're trying to predict the price, basically. I'm not pricing a total in absolute value, but price per foot. Otherwise, you cannot really compare. Because for the most part, like buying a house in Brooklyn, it's going to be more expensive than a condo, smaller studio condo.
Yeah.
That's by definition. And that's what kind of shows them about. Basically, there were the bigger apartments are with some adjustment of popularity or trends of the given area. But Upper East Side, the impact of the tree, even having access to Central Park, it's not going to be as huge as it shows on the map. It's just a matter of that those apartments. That is a very luxury area with bigger, much more expensive apartments than anywhere else in the city. It's just that shows up. But if you switch to per square feet,
Yeah.
this map might look very different. Like, cool concept, cool idea. I think that's fundamentally wrong. Valuing it more. Let's give it up. It's a year. It's more about encouragement rather than just make it.
Okay.
Shit, you can check
Yeah.
it. Or,
Yeah. Okay. Okay. Thank you so much. Thank you for your explanations.
I think Jody raised the hand.
Hey again. Yes, I was also thinking about what was that Colin who was talking about square footage I appreciate all the work you've done, and I'm thinking like, how can we make this better and usable? Because it's really interesting and very exciting that all this data that the city collects is being put on open data so people can look at it and use it. But I want to go back to the tree census. The New York street tree map literally only has trees on it that people have surveyed a decade ago or that Parks has done work on. And I like that you brought policy into it, but the policy problem is that for the last 50 years, mayors aren't willing to pay the price to have street trees. The parks budget has been cut for the last 50 years. So community boards request, but the city council and the mayor reject those requests. The parks department says, we agree, but don't have funding to accommodate. So I'm thinking about how could this be used to provide testimony during budget hearings to advocate for more street trees, because you said a really important thing. They're marked as planted, but that doesn't mean they're still alive. So I was wondering, have you thought of any ways that this data could be used to change policy? Or am I too far ahead of you at this point?
Thank you for your suggestion. Definitely, Judy, you're far away from us. And for most of the policy side design from me, it is my volunteer experience together with different communities from different parks people. So I would say with my conversation with them, I can tell there is a gap, and it is somehow the gap between different stakeholders and the gap between how they manage the tree from data level to a real world level. So I think, your question is really helpful for us. It gives us a very new angle to see it from a city council level, or even people with more power to make a act over the trees. Thank you.
And I just want to validate your volunteer experience. I've organized tree care in every single community board in the Bronx, and I am now retired, and I currently steward multiple parks and multiple street tree beds. So it is volunteers who are standing in the gap between the data and the reality. So I really appreciate that you, even from what you've done as volunteer, you got that, because that's a big message that many people don't understand. There's a big gap. And it's people like you who volunteer, people like me who volunteer, that are filling that gap.
Thank you so much. Okay. Yeah, I think we are running out of the time.
Yeah, I think also we have Max here. Max is also a member of this project. Max, do you want to briefly introduce yourself?
Sure, now that the time is over. I'm sorry for showing up late, but yeah, I'm Max Legalis. I'm an adjunct at NYU, and I also work in city government, and it's been really exciting to see all the amazing work that Archie has done on this project. Great job, Archie. This was a great presentation. Thank you.